Alright, everyone. Testing this. Still not working. Okay. So we are going to be doing Chapter 8, 1, 2, and 3 notes together. Make sure you have those in front of you, as well as your homework sets for Chapter 8. Right now I'm going to go through and do a little bit of review over Chapter 7. So please stay with me. Now, if you have any questions or comments, you need to pause, write that down, because you know that we can't work together until I'm back after the baby or when I get a chance to FaceTime the class. So, stay with me. Here we go. To find empirical formula given percentages, you need to go through and you need to change everything to moles. So here we go. 2 T-charts. Now for iron, you need to, for iron, you need to find your molar mass. So find your green sheet. And sorry, it took me a minute to find mine. Oops. Iron is 55.85. That goes on the bottom. That's 1 mole. When you divide these two, you should get roughly, I think, 1.14. Let me double check my math. 1.14. Yep, 1.14 moles of iron. And then we're going to do the same thing for sulfur. Oops, change that to grams of sulfur. For sulfur, it's 32.07 grams per mole. When you do that one, you should get, again, 1.14 moles. So guys, look at it. If I divide by the smallest, this is going to be what kind of ratio? 1 to 1. Your formula is FeS. Now, for succinic acid, it's given us the empirical formula right here. Then it gives us the molar mass. Well, we need to see if those match. So I'm going to take this and find its molar mass. So I'm just going to round to 12 times 2 plus 3 times 1. Oopsie. Plus, well, let me go ahead and do that. That's 24, 5, 6, 27 plus 16. So that's 30. That's not right. Hang on. That's 24 plus 3 plus, 32. That's the problem. That is 59. Now, if I take my molar mass, or my molecular mass, or my formula mass, and I divide by empirical mass, I get my multiplier as 2. I'm going to multiply this whole carbohydrate by 2 to get my real formula for succinic acid, C4H6O4. Now, hopefully you can remember all this. We shall see. Alright, chemical reactions. So we're going from formulas to reactions. Chemical reaction is where one or more substances are changed into one or more different substances. The stuff on the left side, what you started with, are called reactants. What you'll end with are called products. And a chemical equation shows symbols and formulas, the identities and relative amounts of everything in it. So here, you have a reactant, ammonium dichromate, yields the products nitrogen, chromium 3 oxide, and water. Here, we see this arrow is read as produces or yields, but in our world, it could also mean reacts to form, write this down, or it could mean decomposes into. It just depends on what we're talking about. Alrighty. So what's causing these reactions? We could either be mixing things together, we could be adding energy, like in heat, like either heating it up in a test tube or, cooking something or running a current. Lots of ways to make these reactions proceed. Here are 4 indicators of a reaction. Evolution is energy, production of a gas, what we usually call bubbling, color change, or formation of a precipitate, and that's the solid that falls out of 2 liquids being mixed together. Alright, 8-2, guys. 8-1, you should be able to answer your homework set by now. Do your best. One thing I do want to talk about before we start on this is the how to count atoms real quick, because we're about to get in that really deep here in a second. So if I say chromium 3 oxide here, and it's chromium 3 because we had to switch the charges, and oopsie, please ignore that. Let's say I put a coefficient of 6 out in front. How many chromium atoms do I really have? Well, you would multiply those, so I really have 12 chromium. And then how many oxygen do I really have? Well, what's 6 times 3? I really have 18 oxygen, okay? So keep that in mind, okay? Now, when we're doing these reactions, stuff doesn't magically disappear or reappear. The world of magic is not real. What we are going to do here is called the law of conservation of mass. Somehow things are either being moved around or reconnected in new ways so that atoms are neither created nor destroyed. Now, it's pretty hard to keep up with, but you should be okay. When the same number of atoms appear on both sides of the equation, you know it's balanced. Therefore, following the law of conservation of mass. So how do we make sure they're balanced? Well, the only way to balance an equation is to put coefficients in front of the formulas, okay? It's not the same as a subscript. So let's look at this example. If I put hydrogen gas and oxygen gas together, I can form water, but it has to be in the right quantities, all right? Look here, I have 2 hydrogens, and in the end I have 2 hydrogens. But when we started I had 2 oxygens, and on the right I've only got 1. That's not possible, guys. Not possible. For this to work, I have to balance with coefficients, and what this means is I have to have 2 hydrogen molecules, so these are all H's, and I have to have 1 oxygen. And when those come together, they do so in this fashion. Look like 2 Mickey Mouses over here, okay? Here are the 2 that go with this oxygen, the one on the left, and here are the 2 that form with the oxygen on the right. For atoms to not be lost or anything or gained throughout a reaction, you have to make sure you have the right number of starting things and ending things. It's like if I wanted to bake a cake that needed 2 eggs. Well, I have to have 2 eggs per box of mix to get 1 good cake out of. If I only have 1 egg, I can only use half of the cake mix for it to work out. Ooh, well, never alter a subscript when trying to balance. Why? Well, guys, when you try to just slap a pretty little number or at the end of this O right here, you're no longer making water. What are we making? H2O2 is hydrogen peroxide. I don't know about you, but I do not want to put hydrogen peroxide down in my stomach to make beautiful little messes of my intestines and everything. It would not work out very well. So keep that in mind. Changing a subscript changes your equation. Here are 2 examples of how to balance. I'm going to quickly go through these, but I want you to pause right now and you try to do it, and then I'm going to come back and answer. Okay? All right, for me to balance this first one, I want you just to start left to right. Look at zinc here. Then look at zinc on the right. How many atoms on the left? Got 1. How many on the right? I've got 1. They're happy. Let's look over here at hydrogen. On the left, I've got 1. On the right, I've got 2. Fix that. All you can do is add numbers out in front. So I can't add anything to this right. I have to add to the left. Now I have 2 hydrogens. But look who else that affected. Look at the chlorine now. How many chlorine do I have? I had 1 initially, but now I multiply it by 2. So I've got 2 chlorines on the left. Oh, well, that just happens to balance the chlorine on the right. We are finished with just a 2 in front of HCl. Okay? On the next one, start at the nitrogen on the left. There's 2 here. How many are on the right? Well, just 1 in the ammonia. So I'm going to stick a 2 in front of him. Well, that fixed nitrogen, but now how many hydrogen do we have? Don't add, guys. Multiply. 2 times 3 is 6. The only way to get this to equal 6 is to put a 3 in front. So that's pretty simple balancing, right? We're going to keep trucking, so stay with me. I'm going to put these 2 rules up. Anytime you want to balance polyatomics, do those as single units. Don't break it down, and I'll show you that in a second. And then the next one I'll show you is when atoms show up multiple times. So this first one, let's look here, and here's your polyatomic, your SO4, your sulfate. Count those as 1 sulfate and 3 sulfates. On the left, I only have 1. If you look, there's no coefficient outside. And on the right, I've got 3. We'll fix that first. Just slap a 3 over here on the left. Then look, who does that affect? That affects potassium. Now he has 6, so on the right he's got to have 6. Who did that affect? Well, bromine. Bromine's got 6 on the right. I've got to get him to get 6 on the left. What number times 3 is 6? That's right, 2. And then check out aluminum. I got 2 on the left, 2 on the right. Everybody's balanced. Okay? Again, look at the SO4s, the big bodies, as 1 unit and start there. Next one. Ooh, you see this oxygen right here? On the left? And then the 2 on the right? That gets tricky, okay? If you start left to right, carbon has 1 on the left, 1 on the right. Hydrogen has 4 on the left and only, 2 on the right. We got to fix that. Now he's got 4. And now we'll look at our oxygen last. Well, I've got 2 here and I've got 2 here. So I've got a total of 4 oxygen on the right. How do I get 4 on the left? Just stick a 2 out front, okay? That's how you balance those. Now, 8-2 homework is all balancing. If I assigned your class all of them, do remember number 3, nope, sorry, just kidding. Number 7 and 13 are a little difficult, but be patient on those.